Okay, so again, the notion of slope in space is captured with a so-called direction vector. We no longer have a meaningful idea of slope. Like you can't just capture slope with a single number anymore when you're in three-dimensional space. You know, in two-dimensional space, that was okay because you basically only had two ways that you could travel horizontally, namely to the right or to the left. You could travel in the positive x direction or the negative x direction. And so you were able to describe slope with respect to just moving to the right in the positive x direction. And the slope is basically the amount of y movement for every unit of x movement. That's what it was. But now when you're in three-dimensional space, you can no longer do that. You have to use a vector to show you which direction to go, which direction like a line goes or what's going on in terms of movement from a particular point. We didn't just talk about the parametric equations though. We also talked about the symmetric equations, and even before that, we had the so-called vector equations of a line. The vector equations of a line were like x, y, z. If x, y, z is a point on the curve, like we kind of turned that into a vector. We made like a little triangle, if you'll recall. And what we did is we said, and I'll show you a picture of this just to remind you. You said, okay, I'm going to think of this vector or this point x1, y1, z1 as emanating from the origin plus any multiple of the direction vector. And then basically, when we distribute this t through here and combine things, we end up with the so-called parametric equations. Okay? You basically you see that x is going to be x1 plus at, y is going to be y1 plus bt, and z is going to be z1 plus ct. Okay, that's kind of what we were doing last time. And do you guys remember how we moved from the parametric equations to the symmetric equations? What did we do to move from the parametric to the symmetric situation? Yeah, we just solved for t. Exactly right. Solve for t to move from the parametric to the symmetric. So to move from the vector to the parametric, you simply distribute the t and figure out what x, y, and z are, and that gives you the parametric. So really, you go from vector to parametric, and then you go from parametric to symmetric. Yeah, and so you can go back and forth between these three versions of the equation of a line. Okay. We'll do an example here in just a minute, but I put this little link to GeoGebra in here, and namely the three-dimensional version of it. It's a very, very powerful three-dimensional graphing calculator. So what I wanted to show you was basically a picture of what we were talking about last time. So what I've done here, okay, is I've kind of created the vector equation of a line right here. So what this junk is right here, okay, let me just kind of point out what this is. So this is how you notate, even if I put t in there, by the way, if I put t times 2, -1, 3, it changes it to lambda. It uses the Greek letter lambda for that little parameter. Okay, that's just what it prefers to do. Okay, so basically what I have here is I'm saying that I have a point P, which is 1, 2, 1. Okay, which basically is sitting right here in the picture, by the way. Okay, and then I have a direction vector. Okay, I have a direction vector V, which is 2, -1, 3. Okay, and the vector equation of the line is going to be x, y, z, okay, where x, y, z is any point on the line, equal to this original point thought of as a vector plus any multiple of the direction vector, 2, -1, 3. Okay, and this little graphic down here, I'm gonna animate this here in just a second. This little graphic down here is what's going on with that. So let me move this thing around so that you can see. Do you see P right here? P is 1, 2, 1. Yeah. And then I drew the direction vector moving from there. Okay, so this vector, if you think about it, how much movement happens? So Q is the end of this vector V. It's the one that's purple right here. Okay. How much movement is there in the X direction? Well, 2 units. How much movement in the Y direction? -1 units in going from P to Q. And how much movement in the Z direction? Well, 3 units. So V is equal to, right, this V right here is equal to the directed line segment from P to Q, which is 2, -1, 3. There's my direction vector right there. And then what I can basically do is start taking multiples of that direction vector and recording the end of that. But I have to add together the black vector that goes out to P. Okay, do you see P right there, 1, 2, 1? I have to add the black vector which goes out to P. Do you see that black vector right there? I kind of think of that point P, 1, 2, 1, as emanating from the origin, okay, so that I can use vectors to help me out here. And then what we're going to do is we're going to take multiples of the direction vector and add it to that vector P, and that's going to give us this point R. R is going to be a roaming point anywhere on the line. Okay? And I can kind of animate this thing like this. So do you see that? See how that triangle kind of changes? TV just means a multiple of the direction vector, and I'm adding the black and the red vectors together to give me the green vector. Okay, and I take the terminal point of that, which happens to be R, and that's going to give me any point on that line, right? I could change the range for what the multiple is if I really wanted to, so that it like continues to go out further in either direction on the line. Okay, so V is the direction vector. Then I take multiples of that, TV, add that to the vector going from the origin to P, and those vectors added together gives me the green vector, which gives me the point R, which is just any point on that line as I let T vary. Okay, does that kind of make sense? That's sort of I think that's kind of a neat little animation for sure. So do you see this right here? Here's the parametric equations of that. You can see why that happens to be the case, because if XYZ is equal to 1, 2, 1, right, which is P thought of as a vector, plus any multiple of the direction vector, 2, -1, 3. Again, this is the vector equation of the line. Then what I can do is I can distribute the T as we talked about. Okay, and I can see that this is really just 1 plus 2T, yes? Okay, in the X coordinate. What would it be in the Y coordinate? So it's going to be 1 plus 2T. What would it be in the Y coordinate? 2 minus T, comma. And what about in the third coordinate? 1 plus 3T. Okay, so I mean, you can see X, Y, Z is equal to this. And then all I have to do to get the parametric equations is equate X, Y, and Z. You see that X is 1 plus 2T, Y is 2 minus T, and Z is 1 plus 3T. And I just let T be any number at all, okay? And that's essentially what you see down here, correct? I said I let T go between -5 and 5, but I could have let it be anything after all. Okay, and what about the symmetric equations? What about the symmetric equations? How would I get those? Do you remember how I get them? Solve for T. So how do I solve for T in the first equation? What do I get if I solve for T in the first equation? X minus 1 over 2 equals T, which is also, okay, what do I get if I solve Y? Solve the Y equation for T. Y minus 2 over -1. And what if I look at the z equation? Z minus 1 over 3. Now, what do you notice here? Look, don't you see the things that we're subtracting? 1, 2, 1. Do you guys see that that's the point P? Yeah? That forms the coordinates of the point P. So the things that are being subtracted by x, y, and z respectively form the coordinates of the point P. Yeah? What other information can you immediately get from the symmetric equation? You see the denominators? 2, -1, 3. What's that? What is that? 2, -1, 3. That's the direction vector, right? So the stuff that's being subtracted by x, y, and z respectively in the numerator, that forms a point on the curve, yeah? That makes sense because after all, if I plugged in x equal to 1, y equal to 2, and z equal to 1, these would all be equal to 0, yes? That it would be equivalent to the case where we plugged in t equal to 0, okay? And on the bottom, you have the coordinates of the direction vector. And that makes sense because we divided by a, b, and c to get the symmetric equations, right? So the denominator numbers are just the respective coordinates of the direction vector, yeah? Okay, any questions on that? Questions? I'm going to pause this thing here. Let's see. Doesn't slow down the machine. Okay. All right, let's go back and we'll talk about planes for a minute here. Okay. So a plane containing a point x1, y1, z1, okay, and having normal vector, that's a new word. Normal vector, you should think of this as a perpendicular vector. Okay, yet we have yet another word for perpendicular. This is a perpendicular vector to the plane. Okay, so it's a perpendicular vector to the plane. Okay, n equal to ABC. We use the same letters that we did for the direction vector and lines, but this is a perpendicular vector to the plane. And it turns out we can use that to actually come up with an equation for the plane. We really just need a point and a vector that is perpendicular, and then we're able to actually write down the equation of the plane. How? How are we able to do that? Well, like this, watch. What you do is you imagine this plane right here, okay? And what you do is you say, well, I know that I have this point x1, here I'm gonna use red here just so we can see it well. x1, y1, z1, okay? And I know I have a vector that is normal, okay? So that is, it is perpendicular to this plane, and I call that n, which happens to be A, B, C. Now, how do I describe any other point in this plane? I don't know, let's give coordinates to this point, maybe x, y, z, okay? Well, what you do is you actually form a vector between those 2 points. Okay, you kind of go like this, and you think about this vector right here. What are the coordinates of that vector? What are the coordinates of that vector? So I don't know, by the way, let me just say, let me actually name these points down here. So I'm going to call this point P, okay? And I'm going to call this point Q. So I'm asking you, what are the coordinates of the vector PQ? If it ends at x and it begins at x1, what are the coordinates of the point of the vector PQ? X minus x1, right? So PQ, that vector is x minus x1. That's how much x movement has happened. What about y movement? Y minus y1, z minus z1. Now, Let me ask you a question. What's going to be true about that vector PQ and the normal vector, if indeed x, y, z is in the plane? What's going to be true about those two vectors? No. The plane could be tilted and doing all kinds of weird stuff. They're going to be perpendicular. And if two vectors are perpendicular, what do we know is true about their dot product? It will be 0. So like if I take n and I dot it with PQ, I will get 0. But what does that mean? Well, that means that ABC dotted with x minus x1, y minus y1, z minus z1, that is 0. And lo and behold, if I take that dot product, don't I get a times x minus x1 plus b times y minus y1 plus c times z minus z1 equals 0? Yeah? You see that? That's what the dot product would be. And that's where this standard form for a plane comes from. Okay? You notice, I mean, I want to point out the coefficients of these x, y, and z terms form the coordinates of the normal vector. Do you see that? The number sitting next to x minus x1, that number is the first coordinate of the normal vector, the perpendicular vector. B is sitting right next to the y stuff, and that b is the second coordinate of the normal vector. And c is the third coordinate of the normal vector. Okay? And by the way, if you wanted to kind of distribute, this A and this B and this C and get another form for this thing, you would get like AX plus BY plus CZ minus, let me just write it this way, minus AX1 minus BY1 minus CZ1 equals 0, right? All I did was just distribute stuff, correct? And then what you could do is you could say, well, that's just obnoxious. I'm just going to call all this junk right here, I'm going to call that D. Okay? So D is just all that junk right there. And that's where this equation comes from right here. Okay? You just combine those things and say, well, that's my D. Okay? So AX plus BY plus CZ plus D is equal to 0. Okay? So plus D equals 0. That's the general form of the equation of a plane. So to write down the equation of a plane, you need a point and you need a normal vector. Once you have a point and a normal vector, boom, you have everything that you need. And really it all comes out of thinking about, what it would mean to be in that plane, forming a vector, and realizing that the dot product of the normal vector with that vector PQ has to be 0. And then you get your equation of the plane. Really, this shouldn't be all that surprising to you. AX plus BY plus CZ plus D equals 0. I mean, basically, that's almost like what we had for a line in two-dimensional space, wasn't it? There it was just AX plus BY plus C equals 0, essentially. That was like the standard equation of a line. Yeah, AX plus BY plus C equals 0. Here we just have a CZ plus some other number equals 0. Okay. All right, any questions on that? I mean, we'll get to a little bit more explanation of this in just a minute, but I just want to make sure we're on the same page. Okay, here's the picture. Again, we just went through that. Basically, you think of Q as being some generic point, X, Y, Z, and P, of course, that's the point you started with, X1, Y1, Z1. And then you formed that vector PQ, which was X minus X1, Y minus Y1, Z minus Z1. And that dot product had to be 0, which is exactly what gives us our equation. Yeah? All right. Let's do an example. So example, can you find the equation of a plane through the point 1, 2, 1 with normal vector? Okay, what does normal mean, just to make sure we're on the same page? Perpendicular to that plane. 2, -1, 3. Okay, this time I'm using the normal vectors. I'm using the direction vector from that last example we were working with. Okay, look, this is so easy once you kind of realize where this is coming from. What you do is, remember, it was like ax minus x1 plus b y minus y1 plus c times the quantity z minus z1 equals 0. Yeah? This is going to be easy. You go a, which is 2, right? Because this is, after all, this is a, b, and c. Okay, and this is x1, y1, and z1 right here. Yeah? So it is going to be 2 times x minus 1. Then it's minus 1, which is plus -1, times y minus 2, plus 3 times z minus 1 equals 0. Yeah? And a lot of times it's quite a bit easier to just distribute things and simplify. So like if I were to distribute this 2 and this -1 and this guy here, let's just simplify this, okay? So what would I get? 2x minus y plus 3z. And then what am I going to have? Minus 2 plus 2, and then minus 3 equals 0. Okay, so look, that's 2x minus y plus 3z minus 3 equals 0. There's the equation of the plane. And by the way, you can immediately see what the normal vector is, can't you? How can you tell immediately what the normal vector is? Like if I just gave you the equation of a plane, how could you immediately tell what the normal vector is? Coefficients of x, y, and z. This, okay, there's a little -1 right here, yes, and then there's a 3 sitting next to x, y, and z. So those 3 things tell you that n, the normal vector, is equal to 2, -1, 3. Yeah? So someone just handed you the equation of a plane, you could immediately extract a normal vector. Yeah? And you could easily come up with a point if you had to, just by plugging in certain values of x, y, and z. Okay? All right, any questions on that? I want to go actually, so 2x minus y plus 3z minus 3 equals 0. But any questions on this before we go look at this like in a graphing program? All right, let's go over here. Here we go. Let me get rid of all this junk. I'm going to turn all of this off. Okay. All of this is going to be turned off. Okay. And graphing things in GeoGebra is very, very straightforward. Okay. So here's the XYZ axes. So this is the typical way we see things. X is coming out on the red. Y is going that way, Z is going up. Okay. And we want to graph, what was it? 2x minus y plus 3z minus 3 equals 0. There's the plane right there. Okay. There's the plane right there. That's what that plane actually looks like. Now, one thing that I will point out is it's often easiest to kind of come up with with value or with points by plugging in 2 of the coordinates to be 0 and figuring out what the third has to be. So for instance, if I plug in 0, 0 for x and y, what would z have to be? 1. So in other words, 0, 0, 1 is a point on the plane. If you do this, you will actually get the points on the plane that happen to intersect the coordinate axes. So for instance, this is the place where the thing hits the positive z-axis, right? Let me plug this in. 0, 0, 1. See it right there? Yeah, it kind of popped in there. There's that point, the point we just kind of came up with just now. Okay. Let's plug in some other stuff. So for instance, what if I plugged in y and z equal to 0? What would x have to be? Yeah, it would have to be 3/2. 2 times 3/2 is 3 minus 3 would give us 0, right? So that means another point on here would be 3/2, 0, 0. Okay. And there it is right there. 3/2, 0, 0. You see that? That's on the x-axis. That's where the thing intersects the x-axis. So I have where it intersects the y-axis, where it intersects the z-axis, where it intersects the x-axis. Okay. What would be the last thing that I could do? Plug what? Yeah, if I plug in 0 for x and z, what does y have to be? -3. Right? So that means 0, -3, 0. 0, -3, 0 is another point, yes? So we have just located the 3 places where this plane happens to intersect the coordinate axes. One of them, it intersects on the negative side, right? It intersects the y-axis on the negative side. That's kind of a nice, actually, I think I can make little line segments on here fairly easily. If you go over to this graphing mode, I can make segments. And what you can do is you can go there to there, there to there, there to there. And then you can see this little, triangle that you get in the plane. I think that's pretty cool, right? Okay. So you can do that by kind of flipping over from calculator mode to this graphics mode over here. You can get certain things. You can make lines and all sorts of neat things. Okay. Well, that's one way that we can kind of visualize a plane in 3-dimensional space, is think about where it hits the coordinate axes. It's a helpful thing to do. All right. You guys ready? All right. Let's take this thing. Let's take the quiz. So take out a piece of paper, get ready to go.